part of being able to read these papers is understanding what's important and what's not. This work aims to bridge the existing knowledge gap in the optimization of latency-critical code, specifically focusing on high-frequency trading strategies. The research culminates in three main contributions: the creation of low-latency programming repository, the optimization of a market-neutral statistical arbitrage pairs trading strategy, and the implementation of the disruptor pattern in C++. This repository serves as a practical guide and is enriched with rigorous statistical benchmarking, while the trading strategy optimization led to substantial improvements in speed and profitability. The disruptor pattern showcased significant performance enhancements over traditional queuing methods. Evaluation metrics include speed, cache utilization, and significant statistical significance, amongst others. Techniques like cache warming, Quant's expert showed the most significant gains in the latency reduction. Future directions involve expanding the repository, testing optimizations, etc. Okay. Aims here. Okay. Given the financial industry, particularly buy-side firms focusing on public markets, is secretive, there is not many resources available to guide novice programmers in fields of low-latency programming with a focus on trading. The strategy employed in this research to achieve this goal was to create a bespoke low-latency programming repository containing various techniques. This was accomplished through extensive research and statistical benchmarking. Using this repository, a systematic trading backtest strategy was optimized. Finally, we provide a holistic view of optimization techniques for HFT. News-based trading algorithms are designed to process and react to news events such as economic releases or corporate announcements, aiming to exploit market reactions by quickly executing trades based on predefined criteria. Risk management plays a crucial role in HFT systems by implementing measures to assess and mitigate potential risks associated with high-speed trading, ensuring the preservation of capital and minimizing losses. I mean, until now, everything here is quite straightforward. FPGAs are a type of programmable circuits which are designed to be configured after manufacturing. FPGAs can execute specific trading algorithms up to 100 times faster than conventional computers. Okay, we know all this stuff. This is actually some interesting background information. Let's just read this tidbit. According to the 2017 estimate, all right, 8 years ago, HFT accounted for between, well, this is a wide range, 10 to 40% of trading volume in equities and 10 to 15% in foreign exchange and commodities in 2016. Given the substantial trading volumes and profound impact on financial markets, there's an abundance of information available regarding the economic effects of HFT. However, the literature on computational and technical aspects of HFT is limited due to the secretive nature of the industry and potential conflicts of interests. Fortunately, there are some insights available from industry experts like Coding Jesus regarding their requirements for building HFT software. For example, this, and this. Carl Cook has covered several C++ optimization strategies, including variadic templates, loop unrolling, Quant-expert, and more. This work aims to build upon the existing resources and offer the reader a comprehensive compilation of tested data on the performance of enhancements achieved through the implementations of programming strategies within the applied context of HFT. So let's take a look at these design patterns. This is what we're going to be going into a lot deeper. Design patterns and programming strategies will be used interchangeably throughout this work. As mentioned earlier, there are many ways to optimize C++ code to achieve lower latencies. The strategies that will be examined in this work are as follows. Cache warming. To minimize memory access time and boost program responsiveness, data is preloaded into the CPU cache before it's needed. Compile time dispatch. Through techniques like template specialization or function overloading, optimized code paths are chosen at compile time based on type or value, avoiding runtime dispatch and early optimization decisions. Const-expr. Computations marked as const-expr, or what's the C++ 20 version? What's the C++ 20 version? There's const-expr and there's one more. Or there's one that guarantees compile time evaluation, or it effectively just throws an error. Const eval, yeah. Const eval. Enabling content folding and efficient code execution by eliminating runtime calculations. Loop unrolling. Loop statements are expanded during compilation to reduce loop control overhead and improve performance, especially for small loops, with a known iteration count. Short circuiting. Logical expressions. Cease evaluation when the final result is determined, reducing unnecessary computation and potentially improving performance. Signed versus unsigned comparison. Ensuring consistent signedness in comparisons, avoid conversion-related performance issues, and maintains efficient code. C++ 20 also added a signedness safe comparison method. Who knows what that's called? It starts with the letter C, I believe. Bro, I got a job at IBM. Well, that means you should know this. Nah, not Canada. Yeah, stood CMP underscore, yeah, greater, less, equal. Avoid mixing float and doubles. Consistent use of float or double types in calculations prevent implicit conversions, potentially loss of precision and slower execution. Doubles, yes. And C++ doesn't have decimals. Decimals would be even slower. Branch prediction reduction. Accurate prediction of conditional branch outcomes allows speculative code execution, reduce branch misprediction penalties, and improve performance. Slow path removal. Optimization technique aiming to minimize execution of rarely executed code, path enhancing overall performance. SIMD. Single instruction multiple data allows a single instruction operate on multiple data points, simultaneously significantly accelerating vector and matrix computations. Prefetching. Explicitly loading data into cache before it is needed can help in reducing data fetch delays, particularly in memory-bound applications. Which data structure is very prefetch friendly? Chat, which data structure is prefetch friendly? Hash maps, no. Arrays, yeah, arrays and vectors. Lock-free programming utilizes atomic operations to achieve concurrency without the use of locks, thereby eliminating the overhead and potential deadlock association with lock-based synchronization. Inlining incorporates the body of a function at each point of the function call, reducing function overhead and enabling further optimization by the compiler. Okay, I want to talk about cache analysis because this might be an interview question. Somebody might ask you about this sorts of stuff. Cache analysis. In computer science, a cache is a hardware or software component that stores a subset of data, typically transient in nature, so that future requests for that data can be served more rapidly. The data most recently or frequently accessed is usually stored in the cache, as subsequent reads or writes to the same data can often be completed more quickly. By storing data closer to the processor or the end user, the cache reduces latency and improves I/O efficiency, thus accelerating data access and enhancing overall system performance. Caches are implemented in various levels of computing architecture, including but not limited to CPU caches, L1, L2, L3, disk caches, and even distributed network caches. The term cache hit and cache miss refer to the efficacy of data retrieval from the cache. A cache hit occurs when a data request can be fulfilled by the cache, negating the need to access the slower underlying data store, whether that be main memory, disk storage, or remote server. This results in a faster response time and less resource utilization for the specific data operation. Conversely, a cache miss signifies that the requested data is not present in the cache, necessitating a fetch from the slower data store to both fulfill the current request and update the cache for potential future access. Cache misses are generally more expensive in terms of time and computational resources, and they can occur for various reasons, including the first-time access of data, cold start. That's also called a compulsory cache miss. Eviction of data due to cache size limitations. There is compulsory, there is capacity, and there is compulsory and conflict. That's ineffective cache management strategy. That's conflict. Figure 2 outlines this concept. The ratio of cache hits to total access attempts is often used as an important metric for evaluating the effectiveness of a cache system, and is a metric which is used to work on evaluation of both trading strategy and the disruptor pattern. Okay. Memory access request type read, cache hit, no. Locate a cache block to use, read data from lower memory into the cache block, return data. Yes, return data, done. Write, cache hit, yes, write data to block, write data to lower memory. No, write data to lower memory directly, done. All right, let's talk about cache warming. Is anybody in chat familiar with what cache warming is? 1, if you know what cache warming is, 2, if you don't. 1, if you know what cache warming is, 2, if you don't. Okay, and nobody knows what it is, so let's read it over together. Cache warming in computing refers to the process of preloading data into cache memory from its original storage disk with the intent of accelerated data retrieval. The logic behind this practice is that accessing data directly from the cache, which is considerably faster than the hard disk, or even solid-state drive, significantly reduces latency and improves overall system performance. By preloading or warming up the cache, the system is prepared to serve the required data promptly when it is needed, bypassing the need to retrieve it from the slower primary storage. Figure 3 highlights the speed differences for accessing cache data and different levels of cache. This technique is particularly useful when the data access pattern is predictable, allowing specific data to be preloaded efficiently into cache. Okay, look at how much of a difference it makes. L1 cache, half a nanosecond. Half a nanosecond for L1 cache retrieval. L2 cache, 7 nanoseconds. You're already 14 times slower. Main memory reference going to RAM 200 times slower than L1 cache. Send 1 kilobyte of data over a 1 gigabyte per second network. That is now 200,000 times slower. Send 1 kilobyte of data. Read 4 kilobyte randomly from your own SSD. That's 3 million times slower. In HFT, the execution path that reacts to a trade signal is known as the hot path. Although the hot path isn't triggered frequently, when it is, it's vital for it to run swiftly due to extremely tight time frames HFT operates in. To achieve this speed, cache warming is utilized. Cache warming preloads the necessary data and instructions for the hot path into cache. This means when a trade signal is detected, the system can immediately access the required data from the fast cache memory rather than slower storage mediums, significantly reducing latency and potentially increasing the success rate of the trade. This approach leverages the waiting period in HFT to prepare or warm the cache for instantaneous action once a trading signal occurs. As observed in Figure 4, the execution engine code is not executed every time. Therefore, when it needs to be executed, the cache is not warm. However, in Figure 5, the execution code is executed every single time, but only releases the order when the trade must be placed. That's key. So this is like cache inefficient code in the context of a high-frequency trading strategy. Market data, strategy, execution engine. Market data, and this is like, execution engine, but don't release the trade. Market data, do nothing. Market data, evaluate the strategy. Execution engine, send the order. Right? That's the cold flow. This is the warm flow. Market data, evaluate the strategy. Execution engine, but don't send it out. Market data, strategy, execution engine, don't send it out. Here you actually do send it out. Okay? So here are two scenarios that are tested. Cache cold, cache warm. All right, and then we're going to be they benchmark these two. So what does this do? Generates random indices, okay? And then it sums the data at random indices in this array. Okay? The next one, what it does is it first iterates over the entire array, therefore pulling those cache lines into cache, and then it iterates over the entire array again. So the data is already in cache here, and then you iterate over it. So this measures the latency differences. This is a very, very good question that you might be asked by a hedge fund. Hint, 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 hint. How do I measure cache or RAM access latency? How do I do that? Well, you need to run a benchmark and a test. So what do? You write a program that retrieves data in a random order from RAM, and you measure how long it takes. You might do that for state gives you the amount of runs, so you might do that for 1,000 times. And then you pre-warm your cache and then calculate it again. And what's the difference in the times? The difference in the times is the difference between retrieving from RAM to cache. You're doing retrieve from RAM to cache, and then you're to program registers. And then you're also doing, the next test is from cache to program registers. So you're effectively isolating the difference from RAM to cache. From the benchmark results, it can be seen that warm cache scenario, let's see, let's just look at the benchmark here. Because it just describes here. So a warm cache is over 90% faster. Warm cache is 90% faster. That's a massive speed up. So see what it says here. Interestingly, the cache miss rate remained relatively stable in both scenarios. However, the total number of cache references was lower in the BM cache worm case, thereby illustrating the efficient cache utilization. The difference in execution times between the two systems further emphasizes the impact of cache behavior. The worm scenario exhibited a significantly lower execution time due to more efficient use of the cache, despite the large dataset that likely exceeded any cache level's capacity. The instruction count also increased substantially in the worm case, which can be attributed to the higher number of iterations executed in the same loop, owing to the time saved by reducing cache misses. This experiment underscores the critical role that cache access patterns play in affecting program performance, even when the cache miss rate exhibits only minor variance. Compile time dispatch. Runtime and dispatch and compile time dispatch are two techniques in object-oriented programming that determine which specific function gets executed. What we're interested here is, actually, let's read this part. A distinct performance difference emerges between runtime and compile time dispatch. For the runtime dispatch test, times were 2.6 nanoseconds and 2.5 for derived 1 and derived 2 respectively. In contrast with compile time dispatch, we recorded a more efficient 1.92 for derived and 1 and 2. These data points underscore the efficiency of compile time dispatch, which shaves off approximately 0.68 nanoseconds and 0.23 nanoseconds in execution time, respectively. This has to do with determining which function to call as a result of virtual methods. So there's something called dynamic polymorphism and static polymorphism. So you can use templates to move your polymorphic behavior from runtime to compile time. And that's what they're referring to here. Most very low latency code has no virtual methods because it's not cache friendly. It's not cache friendly because you're going to need to look up that function at runtime via the vtable through the vtable pointer, and then find that function instruction in the instruction cache somewhere. Whereas in compile time, the invoked method is known, and in most cases can therefore be inlined. So you don't need to jump to whatever function exists out there. So CRTP, right? Yeah, CRTP. Now let's look at constexpr. So this is not for dynamic dispatch anymore. It has nothing to do with virtual. It has to do with evaluating functions at runtime or compile time. Constexpr is a keyword in C++ facilitating the evaluation of expressions during compilation rather than runtime. Its advantage lies in enhancing performance by computing values at compile time, thus obviating the necessity for runtime computations. This is particularly helpful for constant expressions with values determinable at compile time. In the present study, an experiment delved into the performance of contrast between two computation methodologies, runtime and compile time computation. So they looked for a factorial of 10, one utilizing constexpr and one adhering to the standard runtime computations. Let's look at the results. Okay, I thought we'd have a nice chart. So effectively, we have a runtime factorial and a constexpr factorial. And we are testing factorial of 10 and seeing how long it takes for both. No, he's not there. Both concepts, let's see here the results. Data showcase a notable performance gap between the factorial functions. The constexpr function recorded a computational span of approximately 0.245 nanoseconds per iteration, while the runtime was more than 11 times more per iteration. These results suggest that constexpr function speed execution exceeds its runtime counterpart by 90.88%. However, it's imperative to mark that this performance variance doesn't imply constexpr consistently amplified runtime speed. The primary objective of the constexpr keyword is to shift computations from runtime to compile time, not necessarily boost runtime velocity. Okay, let's look at inlining very quickly. In computer programming, inlining refers to a compiler optimization method in which a function call is replaced by the actual contents of the function. This procedure aims to reduce the overhead typically linked to function calls such as parameter transmission, stack frame handling, and function return process, right? You need to jump to the entry point of the function. You need to copy the variables into it. You need to allocate a stack frame, and you need to return from that stack frame, thus deallocating that stack frame. Inlining is an optimization that will get rid of all of that. What are the downsides of inlining? Because everything's a trade-off. What's the downsides of inlining? Nothing's free. Nothing's free. What are the downsides? Yeah, larger binary, that's right. Okay, let's take a look. However, it's imperative to approach this method with discretion, and overlines on inlining may inflate the binary size, possibly undermining instruction cache efficiency. Loop unrolling is a technique used in computer programming to optimize the execution of loops by reducing or eliminating the overhead associated with loop control. It's a form of trade-off between processing speed and program size. This technique involves duplicating the contents of the loop so that there are fewer iterations, which decrease the number of conditional jumps the CPU has to make. Each iteration for the loop performs more work, allowing the program to execute faster. In the given test, two functions were benchmarked, one with regular loop and one with the loop unrolled. So see what's being done here? Here, I'm going over every integer in this loop. And because I do so, I'm doing a check. There's a branch here. I'm doing a check. Now, most static branch predictors will assume that most iterations in a loop will be true. But a misprediction will require you to flush all the speculatively executed code, and you will have a bubble in your pipeline. Pipeline bubbles slow down the process of computation and program execution. So here we do +1 every time, and we do this check, 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 check. Here we do more work every iteration. We add 4. The standard loop took around 4,500 nanoseconds. The unrolled loop only took 1,260 nanoseconds, illustrating that the loop unrolling resulted in an improvement of 72.24. However, there are some challenges and considerations. Loop unrolling can increase the binary size, potentially causing more instruction cache misses. The performance benefit can also experience diminishing returns if a loop is excessively unrolled. Furthermore, loops are heavily dependent on memory access speeds, might not benefit from significantly unrolling. Right, everything's a trade-off that necessitates careful analysis and profiling. Short-circuiting is a logical operation in programming where the evaluation of a Boolean expression stops as soon as the final result is determined. For example, in a logical OR A and B, if A is true, there's no need to evaluate B because the overall expression is already determined to be true regardless of B's value. This concept can significantly improve performance by avoiding unnecessary computations. Put a 1 in the chat if you understood that, put a 2 if you did not, because this is the most important paragraph in this section. 1 in the chat if you understood it, 2 if you did not. Okay, essentially what this is saying is if you need to check 2 things and either one need to be true, all you care about is that one of them are true, that one of the 2 are true, right? If I say I'm either A or B, then I don't care if B is false, I just care if A is true. Or I don't care if A is false, I just care that B is true. So which check am I going to do first, A or B? Chat, if I have A or B, which check gets done first, A or B? A, that's right, A gets done first. Now if A is a simple check and B is a expensive check, that's great. We want the simple check done first because there's no point of doing the expensive check if A is true. Because if A is true, we don't care what B is. So we want the simpler, cheaper check to be done first. In the OR and in the AND case, right? Because in the AND case, it's very similar. We have A and B. If A is false, then we don't care what if B is true because false and true is false. So I can skip evaluating B if A is false. They did a no short circuiting and a short circuiting effectively. So either you do A or B, you do both. You need to check both in the non-short circuit case. So as you can see, if you only need to do one, you eliminate the other, you effectively cut down the time by half. Slow path removal. Separating slow path code from the hot path can significantly enhance latency in code execution. In computing, a hot path refers to the segment of code that's frequently executed, forming the critical path in terms of performance. Conversely, slow path code pertains to the less frequently accessed, heavier operations like error handling, logging, or non-critical routines. The principle suggests to modularize and isolate such slow path code from the hot path. This ensures that the process's instruction cache, which is limited in capacity, remains primarily dedicated to serving the hot path, thereby reducing unnecessary cache pollution and context switches. The first code snippet represents a less optimized design where error handling is directly included in the decision structure. The second code path snippet proposes a better design where a function handle error, which is marked as non-inline, encapsulates the slow path operation. This approach keeps the slow path code away from the hot path, reducing instruction cache load and improving overall performance. Let's see what this does. Okay. So here, there's constant checks, right? You're constantly evaluating my slow path. Am I slow? Am I slow? Am I slow? Am I good to go? Here you're saying, tell me if I have any issues at all. If I don't have any issues, go. If I have issues, deal with it later, or deal with it in some way. The benchmark to test this programming strategy implemented two benchmarking scenarios, slow path not removed and slow path removed. In both scenarios, the hot path is hit 90% of the time and the slow path 10% of the time. In the slow path not removed scenario, slow path operations sent to client, removed from map, log message are executed directly. Conversely, in the slow path removed scenario, these operations are encapsulated inside the handle error function, which is explicitly marked as non-inline to ensure it does not bloat the hot path code. I don't expect a massive benchmark increase here. Let's see what it says. Based on the benchmark results, the optimization scenario, slow path removed, exhibits a significant performance improvement over the less optimized. Specifically, the execution time reduces from this to this, indicating approximately 12% performance improvement. The boost in speed arises primarily due to the efficient use of the processor's instruction cache. In the optimized scenario, slow path code is modularized into non-inline function handle error, thus reducing the footprint on the instruction cache, especially during frequent hot path execution. Consequently, cache hits are maximized, resulting in less time spent on fetching instructions from memory. Branch prediction has become a cornerstone of contemporary central processing units, where it functions to anticipate the path that will be followed in a branching operation. When this prediction is accurate, it allows for the prefetching of instructions from memory, leading to seamless and efficient execution. However, a misprediction branch results in a penalty causing the CPU to stall until the correct instructions are fetched, thus hampering execution speed. Interview question. Alarm, 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 interview question. C++20 introduced two, not keywords, what's the right word? What's the right word? Let me get the right word. I want to ask the question the right way. Attributes, that's the word, attributes. It introduced two attributes to help the compiler determine which branch is going to be most likely. What are those attributes? Okay, before I even finish the question, we got Joe here. Joe is right with likely and unlikely. C++23 introduced one more. Do you know what it is? C++23 introduced one more. Assume. Yeah, assume. That's right. In a conventional programming approach, the handling of errors in the execution of the main function, often referred to as a hot path, are often intertwined in a series of if-else statements. For instance, as demonstrated in the first code snippet, each potential error is checked in sequence. Only when no errors are detected does the program proceed to execute the main function. The structure is quite common, yet it presents opportunities for branch misprediction, as the direction of execution could change at any conditional check. In contrast, the alternative approach illustrated in the second code snippet adopts a distinct strategy that fundamentally separates error handling from the main function execution. Here, integer variables, in the case of error flags, is utilized to represent the presence of different errors. If an error is detected, it is handled by a dedicated function handle error, which uses the value of the error flags to decide the specific error handling routine. If no errors are detected, the program proceeds directly into the main function by passing all conditional checks. This presents checks present in the conventional approach. The benchmark for branch reduction consists of two distinct code structures, one implementing the conventional branching scheme, and the other using a reduced branching scheme. The results of the benchmark revealed performance improvements with the adoption of the reduced branching technique. The conventional branching approach resulted in the average execution times of 7.35 nanoseconds per iteration. In contrast, the other one yielded 4.63, an improvement of speed of 36%. Thus, the findings corroborate the thesis that by minimizing unnecessary branches and avoiding potential branch mispredictions, substantial reductions in program latency can be achieved. Prefetching. 1 in the chat if you know what a prefetching is, 2 if you have no idea. Okay, this is really important too. Prefetching is a technique used by computer processors to boost execution performance by fetching data and instructions from the main memory to the cache before it's actually needed for execution. Why might it do that? What property of data is this prefetcher banking on? Spatial locality, that's right. Spatial locality, that's right. Prefetching reduces latency as it minimizes the time spent waiting for data fetch operations, allowing a more efficient use of the processor's execution capabilities. The technique is beneficial in scenarios where data access patterns are predictable, such as traversing arrays, processing matrices, or accessing data structures in a sequential manner. In these scenarios, prefetching can significantly lower the latency in faster code. Analyzing the benchmark results, it is evident that prefetching improved execution speed with the with prefetch by approximately 23.5%. Spatial locality refers to the concept of data that's related to each other being close to each other. Let me give you an example, right? When you are reading, let's say you have a CD reader and the song is 4 minutes and you're on the minute 1. Does it make sense to put minute 1, second 1 data beside minute 1 or somewhere else on the disk that's further away? Right? minute 1 and 1 second, minute 1 and 2 second, minute 1 and 3 second. That data is very close to each other, if not literally contiguous to each other. And what the prefetcher is banking on is the fact that they are close to each other. So it will read the entire chunk, even though you only need the data for minute 1 to be translated to audio. It's going to read minute 1 to minute 1 and 5 seconds, because it's banking on the fact that the data it needs next is very close to the data it needs now. A lot of these questions, guys, are on getcracked.io. Do you guys like this sort of live stream? 1 in the chat if you like it. 2 if you just want me to do behavioral interviews or technical interviews. 1 if you like this, you think it's a good format. 2 if you're like, oh, this is boring and dumb and I hate it and it's stupid. Okay, looks like Mo says it's boring only because he works in HFT.